So the idea was just to show a bit like how do you use the code in practice. So like just basically do a small technical demo, like see, like depending on whatever you want to do, like just ask questions. Basically, it will be interactive. So first off, I can just show you a bit how to actually like get the code and run it. So the main idea is that basically, so this is the GitHub repository. It's all public. You can go ahead and download it. The thing you are probably the most interested in is that part, the packaging, because, well, you can clone the code, install it, and whatever. It's a bit best if you can just like do something like this. And I think it's not even installed on that computer. It will do it. Just install Shamrock. It should work.
Extension for Linux users.
For Linux user, I have options also. Okay, it's already there. So I will show it just after. You have also a SPAC. This one is a bit of an oddity. Most of you probably don't know about it, actually. It's kind of a weird mix. It's kind of a package manager, but for supercomputer. The idea is that basically you will explain how to compile the code when you do a SPAC package on any supercomputer using any toolchain. As a result, any supercomputer that actually use a SPAC internally to actually package the modules have access to any modules within a SPAC. So in principle, if you want to use on your local supercomputer Shamrock, you can just ask your sysadmin to install Shamrock using a SPAC, since it's provided. It should work. I've developed the package. Maybe there are some edge cases that I haven't planned yet, but in principle, you can just ask the sysadmin to install Shamrock, and after that, you can just module load Shamrock and done. So that's one of the other ways to use the code. For Linux users, sadly, the code is not yet in APT or like any of the Linux package manager. So there is a solution, a convenient one that maybe you know, which is Docker. So I don't know if anyone used it already. Probably, yeah. Oh, you really you do?
Yes.
Perfect.
So I am back, so I don't care anymore.
Yeah. The main idea is that if tomorrow you have like any computer, whether it's a Mac OS, Ubuntu, Arch Linux, I don't know, whatever, and you want to run like some code that is absolutely not packaged on your system, one of the ways to do so is to spin, for example, a virtual machine of Ubuntu if you want to run something on Ubuntu. But it's very costly. Virtual machines will be emulating your CPU and whatnot. It costs a lot. A solution for that is Docker, which basically will ship kind of very lightweight system that is just enough to run anything. Funny enough, we can do it on macOS, so you can just do that. I'm on M4 chip, so I have to add that bit to actually tell Docker to run it on AMD64. It will pull the latest version of Shamrock, and then you are good to go. So I have plenty of command, blah, blah, blah. Then what you can do is that you can just run the Docker instance, and you are prompted in, I think it's something like Ubuntu, yeah? Blah, 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 blah. No, actually, it's Linux Kit for this one, but whatever. It's, as you can see, it's a Docker image, so very lightweight virtual machine, but on any laptop. I mean, on any desktop too. So whether you have macOS or Linux or whatever, this will work, provided that you have installed Docker, and Docker is packaged for basically every Linux distro or macOS. So it's a convenient way to deploy it. Anyway, so I can go back because I've installed it. I mean, or we can do it within the Docker. So the main idea is that you will just use the binary. So here I just like start the code. It does nothing because I just did the command. And well, for now we are doing nothing. We are just verifying that the thing starts. Indeed, it starts. Now, has any one of you used the NVIDIA GPUs? You did? Do you know the magic command to check that which GPUs are available or not? I mean, I can demonstrate it actually. Like, I don't know if you are doing something, you know, on it. It will show it. So normally, if you have an NVIDIA machine, you will just log onto the machine and do NVIDIA SMI, so dash SMI. It will show you the list of the GPUs. So right now, you can see that, forget about this one, doesn't exist. That those 4 GPUs are in use, actually. So don't run anything on them. You will crash whatever they are doing. Yeah, you know. So that's the thing. So in Shamrock, we did a very similar utility. You can do Shamrock SMI, so to check the potential machine Shamrock can run on. Here you can see that within that Docker instance, I have only one backend possible, which is Intel OpenCL for CPU, as it's reported here. So in principle, I can just select that device. To select that device, what you can do is that you can just say, well, so Shamrock is using cycle, hence a lot of like terminology is cycle related. So here I want the cycle config 0, 0, hence that everything will be done on device 0. So if you do that, it will instead initialize. As you can see, it tells you which device was selected and tells you that the code in it was done and a random message depending on the time it takes to start. Also, you have additional information on the MPI side, whether you are using direct communication, meaning like communication directly from GPU to GPUs or whatnot. This is more specific. Let's not go into the detail today. Anyway, when you've done that, in principle, so I'm not sure if it works within the Docker container, maybe not. Okay, it does. So here, if you actually want to use the code, one of the ways is to use the code as a Python interpreter, because that's one of the 2 ways to use the code. And you can just pass -- IPython. It will start a IPython terminal in which you can very straightforwardly import Shamrock. And then you will be able to actually use the code. So for example, if you want to start any kind of simulation, you can see that here we can get a model and we have 3 solvers in the code, the Ramses solver, SPH solver as in Phantom, kind of SPH, and the Zeus solver. And that's, for example, how you can start the code. So if you were to initialize the SPH model, I will show it a bit later, but that's one of the ways to use the code. But since everything goes through a Python interface, it means that we can also package the code as a Python package. So naturally, what we can do is also start Python and just this time import Shamrock directly in Python. And this will work too. And the idea is that everything can be done either using Shamrock as a Python package or using Shamrock as kind of the driver. So either you let Python initialize everything and just use it as if it was like AstroPy or NumPy or I don't know. Or you let Shamrock be the driver, initialize everything for you, which is preferred on a supercomputer, of course. Anyway, that's kind of the way to start the code. Then maybe you want to actually run some stuff. So authorize the pull request. So for that, since it's a Python package, it means that we can do a very Python-like documentation. You may recognize this template. You are probably very familiar with this template, actually. It's a Sphinx, the same thing that generates the documentation as for Matplotlib. And if you go into the actual Python API documentation, so this is kind of new in the code, so it's normal if many functions are not that well documented. It will improve as time goes on. If you see something that is weird, undocumented, you have questions about it, just ask or raise an issue for me or anyone to document it. So as you can see, there are many libraries that are exposed. For example, you can go in the SPH model. You will see all the models that are available. In Shamrock, we never recompile the code. This is why we can package it. There is no if-def, nothing like this. So it means that when you install Shamrock, you install the one that can run with the M4 kernel, the M6 kernel, or the M8 kernel. If tomorrow you need another one, we can just add it and done. And then if you go in, for example, any of the model, you will see all the possibilities that are provided. There are many functions. The idea is just to give a very general toolkit and let people basically do whatever physics they want with it. For example, we have, because it's a Python package, it means that we can do the example gallery exactly like Matplotlib does. And we do. So there are some examples. I'm slowly writing some new ones. So this is work in progress. Especially for now, there is no like production, like entire simulation and something, things like that. It's more like example to show the possibilities of the code. I'm planning to add like full production run and how to actually like do the full thing from A to Z. Anyway, so for example, if you want to do very simple stuff, so for example, generate a Gaussian. This is just an example of how to generate a Gaussian using the algorithm library of Shamrock. This is the Gaussian generator I use internally to generate the disk setup, for example. It's in the examples. You can also open a phantom dump, just like this. I mean, here I'm downloading the dump. You can see that actually the code is run in the documentation. So this is exactly what you will get on your laptop if you do the same thing. You can open the dump, actually print the state. So if you want to actually look at what is in the phantom dump, here it is. But that's the very basic thing. Now, maybe if you want to run actual simulations, we can look at what, where is my disk? This one. So this is, for example, a very basic disk simulation. So here you can see that I'm importing Shamrock. If it's not initialized, I initialize it, whatever. I define my unit system. So the units are always relative to SI units. So here I'm just asking for year, astronomical unit, and solar mass. And do stuff with it. I have my parameter files. Here I have the disk profiles that are defined using Python functions that will be passed onto the setup. The setup is directly using the Python functions in that script. I mean, this is called the run script, and for a reason, because it's actually your run is there. Everything from the setup to the actual run to the analysis can be in a single file if that's what you want. Then you initialize the context, which is the thing that holds the data. Like all the data of the code is stored within the context. That's how it works. You attach a SPH model to the context and then configure it. So for example, here I want a constant disk viscosity, which is the alpha type viscosity. Locally isothermal equation of state, as in Laudato Price 2007. I set the code unit, I set the particle mass, the CFL condition, and everything. Basically, this is your input file. Your phantom input file is that thing. And resize my simulation. So cool. My solver is initialized, but I don't have anything yet in my solver. And that's where that magic command enter in. I can just add a thing, literally. So if tomorrow you want a binary, you can just call add sync twice. If you want to put them on a binary orbit, just give the parameter. It will add a binary orbit. If you want an elliptic orbit or any orbits that is not included in the code by default, well, it's Python, so do whatever you want. Then you can actually generate your setup. So for example, I can just use get setup to actually generate the class that will give you like all the possibilities for the setup. Create a Monte Carlo disk generator. So a generator is the thing that will generate the particle for the simulation. You can actually print the actual procedure, like kind of the graph that is used to initialize the code. I won't go into the details, and then just apply the setup. So here, it says that it's pushing data in the scheduler. The scheduler is the thing that handles the data, whatever. It's pushing 1 million particles in that thing. You can change tolerancing on smoothing length and so on, whatever. Let's not get too deep in that thing. You can dump. You can evolve the simulation for a single iteration or evolve it until a given time value. So here, I just say, well, evolve until 10 to the minus 3 as a time value. It will do it. In that example, it's a single iteration, but if not, it will do multiple of them. Then you can get the sync position if you want. Or a bit funnier, don't do this on a large cluster though. You can collect everything that is in Shamrock. And this is actually all the numpy arrays of all the particles that are in the simulation. You can just get them like so. If you want to do scatter plot, specific analysis that is not provided by the code, just get the data, do whatever you want. Not my problem anymore. This is a more like realistic time step loop, the kind of thing that you will actually run. So basically, you will just do multiple event until and just stop, for example, every 10 to the -3. Here, I will do 10 loop. You will dump after each evolve until. Here, this is kind of like the standard time step loop. It will do a few of them, whatever. And then kind of an ODT. You can see a plot here. For a simple reason, it's because it's an on-the-fly plot. You can see that here, I'm just asking the SPH model to render a Cartesian column integrated density plot of the density field. Why is that thing there? Because if tomorrow you have 100 billion particles, splash is not an option anymore. Saracen neither. Therefore, the only way you have to actually render the plot will be to do a plot on the fly. Hence why that module is there. It's actually a ray tracer that is GPU accelerated directly in Shamrock. So the plots are sometimes very fast. Like on 100 billion particles on the Adastra supercomputer, for example, it takes milliseconds to render such a thing. So it's convenient, but it's maybe not as flexible as what Saracen could do. Anyway, so here you have a column density integrated render. But as I said, also if you collect the data, you can do weird analysis. Here I'm fitting some vertical profile to see that the disk is vertically stable. And well, that's the kind of thing you can do. Now, because it's the matplotlib kind of documentation, you can just download the Jupyter notebook. So it will be somewhere there. I will just move it to a new folder. Up real quick. Let's do it here. Whatever. I don't care about this. Up. Let's leave that one. Go into the desktop. And then in the documentation, there is the magic command. I will demonstrate you right now. Where is it? Quick start. At the bottom. You can see that if you skim through the documentation, you will see that thing, the Jupyter Notebook mod. It's a thing. You can actually use Shamrock as in a Jupyter Notebook. So here, don't ask. That command is awful. That's the way it is. It's the way it is for Docker because you have to forward ports and whatnot. I don't care. You can just run it normally. Why does it complain? Blah, 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 blah. Because I'm in the desktop, of course. Stupid macOS. You have always some permission thingy. If I move it here, maybe. Let's see. Blah, blah, blah. Yeah, now it works. So here you can see that I have a Jupyter notebook that is started. In that folder, I go in that folder. I see that I have my basic disk simulation, and well, we can just run it. In principle, if everything goes well. Blah, blah, blah. Where is it? Run all cell. Here. Here we go. So here, as you can see, it initializes Shamrock, change the log level, initialize the units, parameter, blah, blah, blah. Here, it's configured the solver. It's exactly the same thing. I downloaded the Jupyter notebook from the website. It's literally the same. It is actually running. Where is it? Yeah, it's applying the setup right now. It's converging the smoothing length. Up. Is it done? Is it done? It is. Oh, no, it's actually converging right now. Of course, because here I'm emulating like kind of Linux on macOS, you get a slight performance penalty. I want to ship also like ARM 64 Docker container just so that you don't get that performance penalty on macOS, but whatever, it's what it is for now. It's actually running, it's doing stuff. I got the data in my nice NumPy arrays. Blah, blah, blah. It's running some steps. And you should get the column integrated entity in a moment. Is that part done? Probably. Yeah, it's probably rendering right now. Yeah, exactly. And here we go. And that's how it worked. Basically, that's the way to use the code. So we are working a bit on examples. Some of them are dirty. If some examples are broken, it can be completely normal. It's a work in progress thing. But as you can see, we have some examples in the code. The interesting one is plot test. It's the one that do rendering on the fly while it's actually doing the simulation. I can show you that too. Some Zeus example, some good enough example. There is some interesting one also in the actual CI test. It's the thing that I run on GitHub every time. For example, you can do an actual tube good enough with adaptive mesh refinement if you want. It's in the code, so you can. But yeah, that's the kind of thing. I have a few examples. So for example, don't worry about the file name. Here I'm just launching like the plot test example. So it's running actually. It's doing some iterations. This one is was compiled natively on that laptop. So of course it's way, way faster. And now if I actually go in the directory, you will be able to see the iterations. Yeah. I just have to sort by name. And yeah, it's actually doing it. And okay, yeah. This is on my local branch. There is an offset added to the disk. Don't worry about it. But here you can see that it's running and that the plots are actually like generating as we are speaking. So very soon, like there should be okay. There we go. Plot 6 appearing and so on. And that's basically how the code works, the kind of workflow you will have. Just the last oddity before I leave you with this. The setup thingy is way more versatile than what you could think because it's actually a bit more complex. So let me remove this. So this is something we've crafted with Cheryl this morning. Here you can see that I will just show you this. So this is, for example, the actual setup I'm running right now. Can I zoom? Yes. So this is an example of a Shamrock setup. You can render the graph. As you can see, I just like copy pasted that thing here. Soon I will also add like the actual quantities that you use for every module. But here I generate, I generate my disk. Combiner add is just something that takes multiple setup and just like combine them together, let's say. On the other side, I have a HPC, so generator. It's just a cubic lattice. I mean, an hexagonal lattice, a cube with an hexagonal lattice in it. Modifier filter is just something that will filter out particles depending on the criterion. And then I will just add an offset and a velocity to it and just then combine it. And well, that's my simulation. Just so that I show it. This is actually how it's written in the code. So this is my disk generator. Here it's my HCP lattice. As you can see, my HCP lattice is given to, I will zoom in a bit, is given to that filter, which take as a parent the generator that is the lattice, and the filter, a function that is whether or not your thing is in the cat. On the other side, you will take the result of the cat and add it position and velocity offset. And then you will add your cat that is translated to your disk setup and actually apply that setup. If you do so, you will obtain something that is very nice, which is that thing. So I present you a cat and a disk. Just so you see the actual function is a cat is just that thing. It's a Python function. Here I get the point that is given to me by Shamrock, and I just basically return a Boolean that is whether or not my point is within the cat. So here is the cat, and then if you go away, zoom, then if you run the simulation, you will see that your cat will be obliterated by the disk. Very sad. I'm sorry. But it means also that you can play the simulation in reverse and see instead a cat grow out of a disk. Nice. And basically, this is how you can use the setup, the kind of versatility of it. You can combine whatever node of the setup with whatever node. Just think of it if you want to rescale something. If you want to do a spheroid, sure, just generate a sphere, elongate it, do some stretch mapping, make it back into a sphere. I don't know. It's up to you to find how to play with that thing. And we plan to have also some kind of like very similar API for the solver itself very soon, such that you can just basically like connect whatever you want with whatever in the solver. Yeah, and that's the kind of idea in the code. Anyway, and that's it.
Like a formal run through of how to do this, but we can still take questions, I guess. Somebody has questions? I'll ask a question. The Python.
Yeah.
You've exposed the main loop of the code in Python.
Yeah.
Are you worried about users then, like, I want to do something else, I'm just going to tell you this in Python, where it's slow, and then like ruin your performance?
Actually, this is quite okay because, I mean, so I just go back to that example, for example. This is actually the thing, is it the test for with the cat? It's the test with the cat, of course. So here, what I do is that basically the main thing that you are calling, the main thing that will take time is evolve until. And that thing is basically, you will call it like, I don't know, once every minute. Imagine you want to do a dump per minute in average. You will call it once per minute. So once per minute, you will basically go out of Python, like be within the code, like the code is in C++. So you will stay within the C++ for about a minute and then go back to Python. So the performance penalty is basically null as a result.
I'm not worried about the shift from Python into C++ and back. I'm worried about a user coming and saying, I need to do my specific user application. I'm going to avoid C++ because that's complicated. I know Python. I'll put my complicated stuff in Python, and then all of a sudden it's really slow stuff that's running in serial in Python.
It depends. So, I mean, of course, like the main solution to avoid any issues is to give a shitload of examples, just so that like you have so many examples that basically you can pick like whatever you need and don't need to reinvent the wheel. In general, I'm thinking that, I mean, for the setup, it can be a bit of an issue because if for example, if my cat function here was insanely expensive, it would be slow. That one is actually already kind of slow. It's one of the issue. If it's only the setup, is it too bad? Depends. In worst case scenario, I mean, the goal is also to have a community to be able to ask questions too. Right. So the idea is more like to give tools. Try to give the right tools such that you don't need to reinvent the tools yourself. But if one is not provided, at least there is a fallback. Yeah.
Anybody else? Yeah.
Is there any demonstration for like submission scripts for like HPC?
Yeah.
Rather than like running it interactively.
Yes. Yeah. I mean, okay. Let's do the easy one. We just need a code, sorry. You see the nicest warning of a supercomputer I know. It's awful. Stuck. So this is, for example, on Aurora. Oh shit, I have to export this before, sorry. It's just because of my stupid config. 04466706. So, I mean, in the ways to use the code, on a supercomputer, one of the way to do that is probably in my history actually. New env. Yeah, will be to do something like this. When you clone the code, you will actually, I mean, I will zoom in, sorry. You will actually run something like this on Aurora. So it's a basically like specifically environment that is specifically tailored for Aurora. So you will just run this, go into it, like source a script. So I will actually do it. So you will just like source activate, and then just type sham configure and then sham make, which basically like does all the weird CMake commands for you. if you are not using the package version, you can do that. I mean, in general, if you want to see the list of machines we support, you can do this thing. This is the list of actual clusters that we support directly within the code. So that's the kind of thing. In some, there are actual submission script example. In general, they tend to be pretty simple. Let's take one of them. Zoop, zoop, zoop. I don't know this one. Oops. No. Yeah. For example, this is a submission script for Aurora. So it's specific for our cluster. The standard like kind of thing I want to run on whatever number of nodes, something. This is Aurora specific. This is Aurora specific. This is Aurora specific. All of that is Aurora specific. The only part that you are interested in is this one. You will just source the activate script because it has the module load inside it. And then you can just like MPI exec here with a weird command, whatever. It's the kind of command that is supplied by your supercomputer to actually run the code. And if you look, for example, in the activate script, this is what it looks like. It does the module load for you. So it loads the correct module for the supercomputer, for the one we support. Here it's, for example, with debug API. This is the CMake command to actually compile the code, but you won't ever need to write this because it wraps in the sham configure command. Yeah, that's the kind of usage you will have on a supercomputer. So here it was, yeah, on Aurora. But on other side, it will be the same. We have also Lumi. And in any case, like if you need a new supercomputer, just ask. We can cook that together. And yeah.
Great. Well, I'm sure we'll learn how to use Shamrock more over the next week. And if you want to use Shamrock, this week is a good time to do it. One, you can ask a person for help. Just like Timothée.